Hi, everybody. Thank you for joining us again at PAW. Our speaker today is Simon Bortz, who's going to speak on FKP meets DKP. Simon?
Awesome. Thank you. So the work I'm going to talk about today is some joint work with Tatiana Toro and Sihui Zhao. I think I listed on the abstract that it was with Moritz Egert and Olisari, but I'm not sure if I'll actually get to this portion. Although that's the most like sort of harmonic analysis weights type stuff. So I have that saved for maybe a different day. Okay, so this work goes back kind of a couple years. I was visiting the University of Washington, and Tatiana asked me a question about these elliptic operators with coefficients that satisfy sort of a vanishing type condition. I don't know if I'll actually get to that portion, but it was something I really wanted to solve for quite some time. I tried quite many things, probably about 50 things. And maybe like the 25th thing is the thing that I'm gonna show you today, but the estimates weren't there. So I also want to say that a big ingredient in the proof today will be some work of David, Lee, and May Baroda, some estimates they have for a Green's function. And that was the sort of the missing ingredient that brought everything together. Anyway, so I'll get to it. So everything today is going to be in the upper half space. You can generalize this stuff. I don't want to really get too much into that. So I have R plus here, and this is Rn, and the domain is Rn plus 1 plus. That's what we're going to call the upper half space. And so we're going to want to solve a boundary value problem of the following type. So it's the Dirichlet boundary value problem for an elliptic operator L. I'll write out what an elliptic operator is very quickly in a moment. So it's a null solution of the operator in the upper half space. It assumes, in whatever sense, some function f on the boundary, which we'll identify with Rn. And then I put this tilde here, and tilde is something to ensure uniqueness, okay? Or among the class of f that we're considering, okay? Or it's some kind of quantitative estimate, typically. I'll be very specific about that later on. So what is L? L is equal to negative div A grad. Think about this in the weak sense. A is a matrix whose L infinity norm is bounded by some constant in the upper half space. This norm is in the upper half space. And for all xt, we can identify x in here and t in here for upper half space points. We have this lower bound, sort of like a accretivity condition. Yeah, so this is what's called a divergence form elliptic operator. Okay, so if tilde is, say, so if the class of functions we're looking at is f is in, it's a continuous function with compact support on the boundary. That's our boundary data. And say we want to have that u of x goes to 0 as x tends to infinity. This is the type of condition that will ensure uniqueness, right? So just think if L is the Laplacian, right? You can always just add the function t to any solution, right? And that gives you another solution, right? So solutions aren't necessarily unique unless you add some other condition. Okay, and this problem is always solvable. Okay, so it doesn't matter. And by always, I mean, doesn't matter the coefficients for any coefficients. This problem is solvable. This is classical stuff here, classical potential theory. Okay, and so I'll say two things about this. First is the thing I'm mostly concerned about is where f is an LP function, and we want to have non-tangential maximal control on the solution. Remember, U is our solution. And so the prototype here is that, say if L is equal to the Laplacian, then U is just U of xt is equal to pt star f of x, right? Where this is the Poisson kernel. Okay, and then this is a radial decreasing L1 function, right? So this convolution, the super over all t, is bounded by the maximal function. That gives you the vertical maximal function bounds, and then the conical one's just a little, maybe a little tricks. So what I mean by this non-tangential max is if x is one of the points in the boundary, then I look at this cone. The aperture doesn't matter, but we at least fix the aperture. This open cone is called gamma x, and the non-tangential maximal function f is at the point x is the sup over, say, ys and gamma x, f of ys in magnitude. Okay, so this is sort of for the Laplacian. This is classical stuff. So these estimates do not hold for arbitrary A. Right, so there must be some kind of structural condition or there must be some condition in order to ensure that you get these LP estimates. Okay, so like it can fail for all P, for instance. And I should say, oh, by the way, A is always real here. Okay, so that's important for the next thing, because if you have these so what you can do here is use the maximum principle. So we have L as linear. We have a maximum principle. And we have a solution for f in continuous functions with compact support. Yeah, on the boundary. Well, that means that if I fix an x, sort of like let's call this a capital X. Okay, so if I fix a capital X here, then these facts here say that the solution map is given by a measure, right? Because it's a bounded linear functional on the functions that are continuous with compact support. So that means the solution U with data f in this space at x is in fact given by integration against some measure. And we call this measure the harmonic measure, or sorry, the elliptic measure. Maybe we should use an L here. So this is the elliptic measure with the pole at x. Okay. Okay, so let's just assume momentarily that this elliptic measure is absolutely continuous with respect to the Lebesgue measure. Then we can write u f x is equal to this integral, and let's call the Radon-Nikodym derivative of this guy k. Okay, then I can write the solution as f of y k x y dy. Maybe I have too many x's here, but we can all overcome that very small obstacle there. All right, so look, so we might suppose that k. So if we want to solve this for LP functions. Remember, we want f and LP. So if this is going to make sense, right, for f and LP, then we expect that k of this function kxl is and LP prime. Yeah, that makes total sense. So this is with dx. Okay, so in fact, we need something. So this is just to make sense of this integral, to make it finite. But if we want if we want to have these non-tangential maximal function estimates, right? And LP, we actually need a property that's a little different than this, right? So in fact, we need that KLX satisfies a reverse Helder. Let me write out the words. Condition with exponent P prime. So a function G, so when I say a local, everything's going to turn global in a second here. This a trick we're going to do. So this is an LQ reverse Helder condition. So if there's a uniform constant, implicit constant here, so this type of inequality holds, and we say G satisfies reverse Helder Q. Okay, and this is for all delta balls.
Missing a power Q maybe on the.
Oh yeah, of course. Yeah, of course. Yeah. Sorry. So there's like a local version of this. It depends on the pole, but we're gonna like we're gonna send the pole off to infinity in a second here, so that we never have to work with the locality. There's some tricks here. Okay, so anyway, just a slight digression here is that this reverse Helder Q condition is related to the A infinity condition. So the A infinity class is exactly the union of all the reverse Helder Qs for Q greater than 1. Okay. And if you have this A infinity condition is looks like this. So constant here, dx. And this is the same kind of average here. And this constant C, the smallest one, is say the A infinity constant of where W is equal to G dx. So I think of the A infinity condition as a condition on measures, not on weights here. Okay. Even though this, you need to have the absolute continuity. Okay, so the class of coefficients that I want to work with is the following. So I'll have to give some like sort of historical overview real quickly here. So remember, A is really a function of x and t. So this is x, t is here. Okay, and maybe I'll write this as A of big X. Yeah. So what is the condition here? Well, I define, I call these alpha 2 numbers, I guess. This is using some other folks' notation, but I'll just use that. So we take the infim over A naught constant coefficient matrices, and we take the average of A minus A naught. A is a variable. This guy has an X in it. Square it, take the L2 average. And where do we take the L2 average? Over the Whitney box that looks like this. So if this is X and this is T, then W XT is a region that looks like this. Okay, so there's related guys that had been studied in the past. The alpha infinities were studied by Dindosh, Peter Mitchell, and Pfeiffer. And that's where you replace this L2 average by the L infinity norm, right? So the distance of this A to a constant coefficient, some constant coefficient matrix in the Whitney box. Okay. So what is the so I have these coefficients now, and what do I want to have happen? I want to have d mu, which is defined in the following way: alpha 2 squared xt dx dt over t. This is a Carlson measure. Okay, so if this is a Carlson measure, right, we say A satisfies the weak Dahlberg-Koenig-Pfeiffer condition. Okay, so now let me tell you what what we did and what has been done, and then I'll get in a little bit into the ideas behind how to prove what we did. Okay, so first of all, Dahlberg posed these two questions. So Dahlberg was a big player in this Dirichlet problem. I think this is in '84. He had shown the L2 solvability of the Dirichlet problem above Lipschitz graph, right? He won the Salem Prize for this. And then shortly afterwards, a couple of years afterwards, he posed these questions. So he asked basically, and I'm going to say this very roughly, the first part, solvability, stable. So maybe I should say LP, solvability stable under, let's say, Carlson perturbations. And since we I won't actually do this, and there's like all these conditions floating around, I'll just keep it, I'll just say this is a condition, a Carlson condition on the distance between two matrices. And you know one of them is LP solvable, and you want to ask, is the other one LP solvable, or is it LQ solvable for some Q? Okay, so so this was resolved by Pfefferman, Koenig, and Pfeiffer, Bob Pfefferman. And what they did in this, so this is, maybe I'll make a star because I'm gonna have another star in a moment. So what they did is they used some clever identity that Dahlberg himself had shown, and like a bootstrapping argument. This is Annel's paper. It's a really difficult paper, but they also introduced some. So this is the FKP, and FKP meets DKP. They introduce some continuous and like dyadic A infinity equivalences, right? So one of them, and the one that I'll use is the following. So a weight W is an A infinity. I'll tell you what they do with this. So weight W is an A infinity if and only if this gradient of the logarithm of W star phi r. This can be a Gaussian or approximate identity. Okay, this is a really general theorem. We square it, we multiply by r dx dr. If this thing is well, W is doubling first in the background here, but and this is a Carlson measure. Okay. So what do they don't actually use this condition in their paper to prove A infinity. Okay. They also have a dyadic version of this, which I'm very interested in. And I feel like, so it was like expanded upon by Buckley in his thesis. And I feel like that's kind of, well, like Sasha, you're here, you can tell us, this feels like the genesis of the Bellman function type ideas, right? So there's some really cool things that go on in this paper. And like, I really like to, one thing I just kind of mentioned is I really like to understand the the interaction between this discrete version and the continuous version better. I don't know if there's a whole lot of literature on this, and I think it would be a really nice thing to understand that better. Okay, so what do they use this? They don't actually use this to show that their elliptic measures are an A infinity. They actually use it to construct a counterexample to show their theorem is sharp, right? So they use it to show something is not A infinity. Okay, so but here we will see that it's also useful to show that the measure is A infinity. Okay. Okay, and then the other thing that Dahlberg asked is the following. So
Simon,
Yeah.
this perturbation stability, is it small norm or just any?
yeah, so all right, it's okay. So they show let me I'll write everything out. Then so we have these two operators L0 and L1, right? And their coefficients A0 minus A1. We could call this like, well, let's not, this thing satisfies some Carlson condition, right? So so if the Carlson, let's suppose that this L naught is LP solvable, okay? Then I'm not sure if they write out the small norm version, but what they show is that if the discrepancy, if this thing appropriately normalized and worked over like Whitney regions and things like this, right? This satisfies some Carlson condition, right? Then I get that L1 is LQ solvable for some Q. And I believe that they work it out where they might work it out. You probably work it. You can probably track the constants in their proof and get that L. If it's small enough, then P is Q. Yeah. So what do they do here? Well, it is a small perturbation argument. It's always a small perturbation argument in their thing. They break up L0 to L1 into like lots of operators, right? So that the discrepancy between these two operators, say, let's call this Ln now, okay? Maybe let me give it a different, let's call it Lk. Yeah, so L0 is L0 and L, say N is L1. Yeah, so they break it up into N steps where each one is very small in Carlson norm. Yeah, and then they show that the elliptic measure, if the step size is small enough, the elliptic measure for one of them is in A infinity with respect to the previous guy. And that's what requires the small norm thing is required there to do this step by step. But the size difference that you need only depends on like the ellipticity and dimension. Yeah. Does that make sense? What they do there?
Yeah. So they prove the theorem about elliptic measure, not about solvability, actually, right? Yeah. Well, I'm sorry.
Yeah. But I think you can track things to actually get that it's like it's the constants and things like this to make sure it's like P is equal to Q if it's small enough. Okay, so all right, let's go back. So Dahlberg asked a second question, and his second question was like, if this guy is the density of a Carlson measure, right? Dx dt is a Carlson measure. Does this imply that the elliptic measure with these coefficients is an A infinity? And this was resolved by Koenig and Pfeiffer. There was sort of like a simultaneous result of Hoffman and Lewis in the parabolic setting. It's like difficult to tell who did what first because they both cite each other. So I don't know if that was intentional. I've never pried the authors for any details, although it has. I'm always curious about it. So notice this like gradient condition here. they have some other condition, right? So like the gradient of A is like less than or equal to like 1 over T. And this condition here will, and yeah, there's actually, this thing is like a soup over some like Whitney regions or whatever, but let's not worry too much about that little detail. So like if you're careful, you'll see that this condition here in the posed by Dahlberg is stronger than it'll imply this infinity guy. This is just Poincaré's inequality. Okay, take the A0 to be the average, and then this guy is, which is stronger than the alpha 2 guys. Yeah. So again, this was treated by Dindosh, Peter Mischel, and Pfeiffer. Okay. So the thing that I'm really concerned about is especially the small constant versions of this. So by the way, no one's treated this. No one's shown that if this thing, okay, well, not no one now. Until we wrote this paper, this condition, which is the weak DKP condition, it was not known whether weak DKP implies the elliptic measure is an A infinity. Okay, so we do that, but we show that smallness of the Carlson measure, this guy, let's call this norm like script C, why not? That's what people use, of this thing, implies that this guy is an A infinity with small constant. And somehow there's like the thing that Tatiana Zihui and I do is, if this thing is vanishing, then it implies the log of this guy is in VMO. Well, it should be VMO loc. So we take care of the large constant, small constant, and vanishing constant sort of all at once. And this small constant thing, it wasn't in the literature, to the best of my knowledge, the small constant version of the Pfefferman, Koenig, Pfeiffer paper. And so that's the paper that I wrote with Oli Sari and Moritz Egger. So I won't get to that. I'll just show you that well, this condition is going to directly control the Pfefferman, Koenig, Pfeiffer condition. Okay, so let's remember a few things. Okay, so remember.
Simon, so do I understand correctly that before your work, the answer to Dahlberg question was not known? Right?
No. Koenig, Pfeiffer solved the Dahlberg question.
Ah, okay. Oh yeah, you said and Lewis was somebody, right? Mm-hmm.
Yeah. This is the elliptic version, and then there's like a Hoffman and Lewis thing that I don't really know. Like they published the same year, and they both refer to each other as giving each other ideas. So I don't know what happened there. Yes. Yeah. So,
but what you did is strengthening, right? It's a different...
strengthening, but also this. So a few things. This was not known, and neither was this. Not even in the case of this condition. So if that was small, it was not known if the A infinity constant was small, and if this thing vanished, whether it gave the log of K is in VMO kind of that thing. What was known, and so I mentioned these folks, they did a small constant version where they showed that you could get whatever reverse Helder constant you wanted. Okay, so a big reverse Helder constant is harder condition to satisfy, but also it gives a smaller exponent for the Dirichlet problem, right? By what I discussed. And that makes sense that that's much stronger because the endpoint is the maximum principle, right? So smaller p for the Dirichlet problem is the hard thing. Yeah. Okay, so let's just recall that a weight is an A infinity if this is a Carlson measure. So if this thing is a Carlson measure, then the weight is an A infinity. If it's a Carlson measure with small constant, this is the work with Moritz, Eggert, and Olisari. This implies small constant A infinity. And if it's vanishing Carlson, then this is work of Corey. By the way, this is FKP, as I mentioned before. Work of Corey shows that this is this shows that log of W is in VMO.
Stupid question. Small A infinity means the constant in the quality you wrote is
The
close,
Khrushchev thing. Yeah.
close to 1, right? The constant.
Yeah. Sorry. Small constant A infinity means 1 plus epsilon. Yeah. So of course, it's not gonna get smaller than 1. Yes. Yeah. Okay. So so that's one thing we know. And also I want to just I want to write out an identity for you that's really useful. So I mentioned this work of David, Lee, and Mabaroda, and what they show is some estimates on the green function. Okay, so we're going to rearrange things here in a second, and we're going to write out an identity that takes our elliptic measure to the green function, essentially. So the first thing I want to say is that there is something called the elliptic measure with pole at infinity. It's like a renormalized thing as you blow up. And if this thing is an A infinity, then it implies that all of the other guys are an A infinity. Okay. This is like, I proved this we proved this in the paper with Tatiana and Sihui. So we can shoot the pole off to infinity, and that way we don't have to work with this local A infinity condition. We can work with the global one, which is the framework that FKP are working with, and these kind of results here are all in. So so we shoot it off to infinity, but we also get a Green's function with pole at infinity. Okay. And now there's this nifty identity, and this is only a function now of one variable because we shot the other variable off to infinity. Okay, which is kind of nice for writing out the computations as well. So I might mess up the signs here, and so I apologize about that. Let me write out the identity. I'll tell you what the players are here. So well, no, I'll just tell you now. So if I have a function that's smooth with ComStack support, and now notice this thing can go over the boundary, right? So there's not a plus on this rn plus 1. It can go over the boundary, and f of x is equal to the boundary data, or the boundary values of f. Then the following identity holds. That thing's gone. That's also another convenient thing. Sorry about that. Usually there's like a Dirac mass piece, but we shot the pole off to infinity, so the Dirac mass disappears as well for these functions. Okay, and now let me write this kind of weird looking computation. So I have the transpose of A, the gradient of G, and the gradient of F. Okay, and this is the G infinity guy.
It's
okay, so this,
it's Rn on the left.
Yeah. So if this pole was finite, right, then and this pole was finite, then I'd pick up a plus f of x here, right? But the pole getting shot off to infinity kills that a little bit. Okay, so we want to use this in this idea here. Okay, So let me show you how you do that. Okay, so the gradient of the logarithm of, and now sorry, my omegas are the same thing, but let's have omega infinity star phi r. This is not it's not a weight, but actually the finiteness of this condition. So this makes sense. This convolution makes sense for a doubling measure, and like everything's going to be, everything here makes sense, at least point wise. Maybe not initially as a Carlson measure, but it does make sense. Okay, so this thing being a Carlson measure will actually also imply that the object here, if it was started off as a measure, is absolutely continuous. So we proved that in the paper with Tatiana and Ziwei. Okay, so this is equal to, well, we know how to differentiate the logarithm. Okay, so we'll get WL star grad phi r squared at x, WL star phi r x squared r dr dx. Yeah, so that's the differentiating a logarithm for you. And now what? So notice this gradient, it's not phi, it's not the gradient of phi approximate identified or what, or like L1 normalized, but it's the gradient of this approximate identity. Okay, so like the whole thing. All right. All right, so now what? Well, let me just say that the denominator, this piece here, let me use a different color. This guy here. So this thing is less than or equal to an average. Remember, this is, I should give you a more precise definition of phi in just a second here. Let's say 2r, why not? Grad g squared. So this thing is with the square, the whole thing. Okay, and there is average. Okay, cool. So that's going to get replaced by that later on. In fact, it's in the denominator. I'm trying to get an upper bound. So I should probably have that it's comparable or bounded the other direction. Yeah. Okay. So so what do we do about the numerator? Well, one cool thing is that, well, this is just an integral, right? So there, I can use the Green's formula, right? Remember this Green's formula here, okay? But I'll just choose like most natural capital phi, okay? So this guy will have a phi here, and there'll be a capital phi here. There'll actually be grad phi and grad x. Spatial, what's grad parallel say? Okay, so what's phi? Phi is like your favorite cutoff function. So you can make it whatever, but mine's gonna look like at least a radial version here. So that's 0, and this is a half, and say it's like constant here. Okay, and that's why this works here, because this here is basically, we're using the doubling condition for this elliptic measure. It's like the elliptic measure of this ball squared divided by the measure of the ball squared. Okay. So what I need to do, so this is phi 1, and phi r is, sorry, 1 over r, phi rn, phi dot over r. Okay, so what do I do? Well, I'll just make capital phi. So this guy, let's call this is integration against some function. Let's call it phi x r. Okay, so the integral of this is equal to the convolution. Sorry. Yeah.
Mhm.
Okay, and now I'm going to put a parallel to mean gradient in this direction only. Okay, just so we know that the gradient doesn't. That's really important in a moment here. Okay, so then I extend this phi xr in the most natural way. I'll just multiply it by this function. Yeah, that's actually not, and it's not modified. It's at height 1 here. You don't want to do like a normalization or it'll change the values on the boundary. So this goes out to like say R. Okay. Okay, so well, what happens then? Some tricks. Okay, so now this numerator, okay, looks the following way. So let me just kill the this thing is equal to the integral of grad parallel phi xr d omega. Okay, that's the thing that's in the absolute values. And so up to a sign, I think a minus sign appears here. I'll have grad A transpose grad G grad phi xr. Yeah, so say dy ds. Okay, so now I don't know what to do. So this is try number 25 and the estimates aren't there. Okay, so it's February of this year, and Svetlana Guy and Lin Han post this paper, and it's estimates on Green's functions with these coefficients, and it piques my interest, of course, as I remember try number 25. So what do they show? They show two things. I'm going to show you. I'm going to show you in action what's going on there. So remember, I showed that this quotient, this one here, the denominator looks like the average of grad squared G. Yeah. What they show is, well, they show something a little different. They show that, but it implies this. So they show that grad squared, this guy, grad parallel squared of G divided by grad of G squared. So we call this beta, and these are on balls BX R intersected with the upper half space. Same here. If we call this thing beta, then actually beta x r dx dr over r is a Carlson measure. And it's completely controlled by the alphas. So the alpha squared dx dt over t Carlson measure constant controls the Carlson measure constant here. Because that's a really good sign, because it means I can ignore all of the parallel gradients in the following, right? So if we look, the reduction I made here, right, or the observation is that this looks like grad squared G, right? So if I just look at I can break this up into the parallel part and the sort of t, where t is this direction, the t derivative, right? So this part is just freebie, taken care of by their estimates. Okay, does this make sense? Mm-hmm. Yeah. So the grad parallel part is just, it's taken care of there. Okay, and then the second part is what do I do with the time derivative? Well, I get even more lucky, because they show that this guy controls, let's put a tilde here, why not? Okay, this Carlson measure controls this one, or what's the alpha tildes, and this Carlson measure constant of this controls this Carlson measure constant. Okay, where instead of, remember, I looked at the I looked at the distance from A to a constant coefficient matrix in L2 norm here, right? In average L2 norm, okay? And now the alpha tildes take this piece. Yeah, so in fact, you can control the whole Carlson region, not just the Whitney region. Okay, and you can think about this. This is not, look, this is the cool, all right, I'm gonna say, this is obviously my opinion. This is the cool thing about this Carlson control is the cool thing about their paper, okay? In my opinion. This thing is like a, you know, a Hardy type inequality, okay? But like they already proved it, so you use it, right? So let's, I messed up something here. There should really be like a extra parallel gradient of this guy here. Sorry about that. Okay, so what are we left with? Well, we're only left with the t derivative part. Okay, so I have throw away the rest, and I have this A transpose dt g grad. And this is why I know that I forgot about this, because I'm going to use that in a second. Okay, so what am I going to do? Well, I'll trade A for A naught, a constant coefficient guy. Though if we, oh, there shouldn't be a G here, obviously. The constant coefficient guy, remember the support of this function is essentially in one of these Carlson boxes. Yeah. So I change A to A naught and I pick up an error. Here I'll use the full gradient of G, right? And the denominator is like grad of G, right? So that part disappears. And I pick up an error, which is like this A minus A naught, but it's in this Carlson region. I pick up an error that looks like this alpha 2 squared guys. Well, without the square, because I haven't squared this thing yet. Okay, that's also sort of for free from them. And then, well, it's not so hard to conclude, because now if I can replace this with a, so this one's constant coefficient. If I have constant coefficients here, well, I want to get a grad parallel. I apologize. You can break up this grad parallel into the like its components if you really like, because this is kind of confusing. This should be dy ds. Okay. But now it's constant coefficient. So I move this over here, right? If you look at where this function vanishes, right? G vanishes here, and the product vanishes also up here because of the support of this this VXR guy. Okay, so I can integrate by parts, and in T I pick up 0 boundary values, right? And now similarly, I can integrate by parts this parallel gradient, right? Because this support here, it's supported in this box, so I can pick up no boundary terms now. And then I basically get this grad parallel G term. Okay, I can write out exactly what it is. Part of this gives you an average. Another one gives you like a 1 over R. This is over Bx R intersect the upper half space. What's a 1/2? So it looks like this. And that's exactly the kind of thing we want to work with, right? So actually, you know, I pick up some of these R's here. I didn't really track the R's for you. I hope you're not too worried about those things. Always take care of themselves, right? And so that's how you take care of the rest. So that proves that essentially locally you get a pointwise inequality that's this. I think it's very cool. It's a pointwise inequality. Maybe I'll write out the thing I started with. So this density here okay, is less than or equal to 1 over r, this beta xt thing I defined, plus 1 over r. Well, these are like dx dt's, xt or xdr, and then this alpha tilde to xr dx dr. So in fact, you get a pointwise inequality by these two things. There's some constants that depend on ellipticity dimension, but so it's a pretty cool thing. I think so. Like from this, since the alpha 2s, sorry, there should be a squared here. The original alpha 2s dx dt control this guy, not pointwise, but they control this guy in Carlson measure. So they control this guy in terms of Carlson measure with constants that only depend on dimension and ellipticity. So then the remaining things that I said just follow from the known things and the work that I did with Mortzager and Olisari on the small constant FKP. Sorry, maybe that was a little garbled. I apologize. That was a little all over the place. But I think that's probably a good place to stop. Yeah.
Thank you, Simon. Questions, please.
How about the previous slide? I don't understand why you have gradient twice. Yeah,
Oh,
yeah, exactly the first line of the
this thing?
Yeah.
This one's the numerator, right?
No, yeah. Well, like next line, you have AT, gradient G, and then gradient phi. Why gradient?
Yeah. So remember, let me refer you to this. So look, this is a weird quantity because this is a, let me write, this thing is a vector, right?
Yes.
Okay, so this thing, you should think about it as the components are these.
Oh,
like,
yeah, and then the second gradient is from formula. Okay.
Yeah, the first, yeah. This full gradient is from the formula, but only the gradient parallel is coming from the FKP thing. And that's how you win, because you always need to have parallel gradients of G. So I think the reason why the David, Lee, and Mabaroda didn't prove this theorem is that they didn't actually write this thing, right? So what does this mean? It means that the G is very close to being a linear function in this transversal variable, right? In some sense, or at least its change is purely transversal, right? But their thing is actually quite a bit stronger than this. So they show, instead of this numerator grad parallel G squared, right? The control they get is actually on, exists some constant so that G, and this is like, remember, this is over like B, X, R, or something like this. So it's G lambda X R, same average, say, of T. Dy ds, say. So, and then you square this guy. This guy. Yeah, so what I'm saying here is that, so this is a crucial observation. So here this really says that G is basically a linear function in T, right? In this transversal variable. It's much stronger than this, right? And the key observation is when you move the gradient on the n side, you're subtracting off a vector that's only in the T direction, right? So that means the parallel direction was already small. Yeah. A big time observation there that does the trick. So like if you get, I think the reason why it was like, so I thought they were going to prove this theorem, to be honest. And because they said they were getting close to doing some of this stuff. But I think what they did is they were like caught up on this very strong estimate where the thing you need is actually a weaker thing, right? Sometimes this happens, right?
But in the definition of A infinity, you're using this gradient log of omega L infinity convolution with phi r. the gradient is in all directions, is it?
No,
No.
no.
Oh yeah. Well, yeah, I'm saying
You're
something.
thinking of the
Yeah,
Pfefferman-Koenig
I'm
or
sorry.
the Pfefferman-Stein thing. The
Yeah,
Pfefferman-Stein thing, yeah. So here's the cool thing about, I always thought this was a cool thing. Another thing I don't understand very well is just what about the doubling condition makes, so like lets you commute the logarithm here, right? So the Pfefferman-Stein, the Pfefferman-Stein like BMO duality stuff, right? This, if it would really want to say, or how do I want to say this? Yeah, I mean, sorry, I want to commute, not this thing. We want to commute, we want to put the log here. We want to commute the convolution, I guess, with the logarithm, if that makes sense, right? Because that's what the Pfefferman-Stein would say. So if you let me put this in red so we don't, if you have this, right, then this is the Pfefferman-Stein thing for log of W. With, well, okay, not the full gradient, but just the parallel guy. So the doubling condition is what lets you say that lets you like sort of commute this action, right? But I don't know why. I like I like weights, but I maybe haven't done too much of this kind of thing with them, right? I'm really interested in this Pfefferman-Stein stuff. There's a lot of directions you can go with this idea too, right? Because notice that this condition here, like this is an equivalent condition to A infinity if this thing is a Carlson measure, right? And like this is always true, right? So it means that
by the way, in the case of discrete things, the dyadic things, this condition is like something like what's his name?
Buckley?
Buckley, yeah.
Yeah.
It's like Buckley, right?
Yes. And that means that like whatever you're going to do, right, to win this game, this thing has to contribute in a way that gives you a Carlson measure, right? There's no way around it. So like it doesn't matter what the coefficients are, right? This is for this problem in particular, right? But essentially, like in every single one of these problems, like all these different conditions, like obviously we don't want to get into that too much, but like for instance, if A is symmetric or real or symmetric and T independent, or just merely T independent and real, right? Those guys have elliptic measures that are in A infinity, and so this thing I circled here in red must be under control in some Carlson sense when divided by the sort of local energy here. This guy. Yeah, so I think like it's worth like looking back at some of this other the previously done things. There's more reasons than one. We could talk about it a different time, but there's like a very nice problem that I'm thinking about that's related to this stuff. So yeah.
Is it stupid to ask such questions not in half half space, but in some domains? Or?
Yeah, I mean, I'm not okay. So like, this is going to show where I don't know a ton about these Carlson conditions, but wherever these things work, there should be some kind of hope, right? Now, the one issue is just going from dyadic to the continuous version. So I feel like these conditions will work. The dyadic versions will work in exotic settings, I would hope. But the continuous version here is very much like an Rn thing. And it's very much what we're using to invoke this green function identity. Yeah, so it would be nice to actually do this to discretize this proof, but I didn't manage to do this. I haven't had time to think about that side of things as well, because that would be another way to do it, right? To run everything through Buckley and or like the things that have come since then. Yeah. But also
denominator, estimate of denominator was important here, and it was probably important that it was half plane, that its gradient G is estimated via the elliptic measure
That should work in like a
in many
maybe a
situations.
uniform domain. Yeah.
Yeah, probably, yeah. Mhm.
Yeah. But you know, if you want to do this thing in like exotic settings, what you do is so like it goes back to the like David and Jerison thing. You use like the maximum principle and you try to approximate. And then you know, the like refinement of this is the work of Koenig and Toro, where they find like if the chord arc constants are really nice for a chord arc domain, then you can approximate in a very large piece with a very flat graph.
Mhm.
And so then it reduces everything to the case of graphs.
Mhm.
But these coefficients have a nice pullback to them, right? That retains this property. You pick up constants that depend on on like, let's say if it's a Lipschitz domain, right? It depends on the Lipschitz constants dimension and the ellipticity parameter. So you can reduce the graph case to the half plane, and then
Yes.
you reduce the chord arc case to the graph case, and like so on and so forth. Yeah. So like that's something else I did with Tatiana and Zihui, but like we did it with a different class of coefficients, and I didn't want to like, I mean, that's like a long paper. I want to write the same paper twice. So I think someone could pick up that paper and this paper and prove that if the measure here, so let's say you're in a vanishing chord arc domain and you have vanishing this Dahlberg, this weak DKP condition thing, right? Suitably interpreted in that setting. If you had those two things, then you would get the log of the elliptic kernel is in BMO.
Mhm. Mhm.
But that's like 50 pages later.
Mhm. Mhm.
50 similar pages to things I've done. So I'm okay with not doing that.
Thank you.
Yeah.
Very nice.
Yeah, thank you, Simon, very much.
Yeah, I hope it wasn't too garbled.
No. It was a very lively. Does anybody else have questions? Okay, well then let's thank Simon again. Thank you so much, Simon.
Thank you, Simon.
And we hope to see you all next week.